Good afternoon, everyone. My name is Sergey. This is Chris, David, and James, and we're presenting our functional final prototype of our handheld thermal neutron radiation detection system. So to remind you how our detector works and the individual responsibilities of the group members, we once again divided our presentation into 4 sections. We'll start with detection. To detect a neutron event, we start by running a diode in reverse bias. The diode is topped with a 10 boron conversion layer, and as the neutron passes through the boron conversion film, it has a chance to interact with that material and produce an alpha particle as a result of the interaction. Once that alpha particle passes through the depletion width of our diode, it creates electron-hole pairs that result in a current spike. We then have to amplify this signal, and we do so by using a charge-sensitive preamplifier designed by Chris. Pairing a diode with a preamplifier, we create what we call a modular detection pixel that you can see right here. Now, we have to be able to identify these detection events. Taven, having worked with Chris, has developed a motherboard that supports 5 microcontrollers and 9 total detection pixels. He's able to recognize the detection event and pass that information along over Bluetooth to an application developed by James. This application supports not only the real-time detection count, but can also delineate that individual pixel that detected the event, as well as provide GPS coordinates for the detection event and even email alerts. So this prototype has seen a full redesign and rethought compared to the last one we showed up during semester 1. One thing we've done is we moved over to a silicon PIN diode so that we could increase our overall detection area. Also, Chris has continued to minimize the preamplifier, which allows us to increase pixel density, which in turn increases the detector efficiency. Taven has stepped up the digital stage, going from 1 microcontroller servicing 1 detection diode to 5 microcontrollers in a master-slave configuration. We're able to expand this design to service more diodes simply by adding extra slaves. Finally, James has also enhanced the user interface of his application. You can see it has a much friendlier UI now, as well as all the additional features we mentioned before. All of this we're able to achieve under the $500 target limit for this device. Actually, ours costs $390 in terms of parts. Now, unfortunately, we can't demo this detector for you here today because we can't introduce a neutron source into the building. We'll have the detector available to see at our booth, and then about starting at 5 o'clock, Taven and Chris are going to walk it over to the Neutron building, where we keep our California 252 source used for testing. They're going to call us in on a video call, and we welcome you to come by our booth to check out a personal live demo, exposure-free. Thank you.
All right, any questions? Can you tell the reason you choose cadmium alpha as a detector?
So that was something that we used during the first semester, and we switched over to the silicon diode. The reason we wanted to do that is one, cost. Like, the idea behind this project is that we would be able to make large area detectors. So we wanted to incorporate that technology in this handheld. Unfortunately, we weren't able to make devices that could be supported by the preamplifier due to the device capacitances. So we actually switched back over to the silicon diode, which increased our area, which was beneficial to the detector. And in this size, it still remains a cost-efficient solution.
So can you compare the 2 different diodes in terms of sensitivity?
Silicon is going to be more sensitive because it's just like a perfect photodiode in this sense. And since the alpha is essentially a light particle, we can detect. So yeah, the silicon is 100% sensitive. Our cadmium telluride can't be that sensitive, but it would be cheaper. And you can't make a large area detector out of silicon due to wafer size limitations. Whereas the cadmium telluride one, if you use a thin film process, you could scale it to very large detectors such as solar cells.
Thank you. Other questions?
So you said that you guys redesigned the preamplifier to have better performance. What's the performance?
So the way we measure it, we use this process of this. We use a 25 volt millivolt pulse, and since that's where the function generator can go, we can't actually simulate the tiny event that we get from the alpha particle, but compared compared to this Vortex system, we are getting a better input. So like our preamplifier is built for this specific purpose. So whereas the Vortex can take much higher device capacities, and so that's what our comparison comes from.
So, what would be the bandwidth of the signal?
The gain.
The gain,
Yes. In our specific application. And again, because it's tailored for our purpose, whereas that one can do much more.
What do you envision the target application is?
So again, this is like part of the overall project that we are a part of. One of the ideas is like, for example, let's say that there's some kind of event where someone smuggles in a radioactive source into the country. The idea is if we can build enough of these small enough and cheap enough, we can put them in like law enforcement officers' cell phones, for example. So throughout the day, as they're going around making patrols, they start to build up a background radiation level that's natural to the environment, right? In the case you're trying to find the source, you have to be pretty close to it. So if you can have a baseline, so like for example, I believe granite emits radiation. If you can find a baseline, then you can be more easily be able to detect your smuggled material above the baseline.
One more question. Can you identify in this whole design project, the shortfall, something you'd like to change and improve on? Or is it perfect?
No, it's far from perfect. We actually have had a lot of problems. Do you guys want to talk about anything in particular? There's some simple design issues, like for example, we wish we put on a power indicator on our motherboard. So it's kind of hard to tell if like we're missing a connection or something.
Makes troubleshooting there.
Yeah. But in terms of like larger design, you actually unfortunately can't see it in the picture. You can see it at our booth. But the way that each detection pixel plugs into the motherboard made it very difficult for us to attach them by hand. So we had a lot of trouble that we put in a couple, we test them, they work. We put in another one, we bump, a wire, a circuit, and the device stops working. So in terms of that, we should have considered the mechanics a little more.
All right, just thanks, Peter.